NASA returned to the Moon with cramped, single-use landers. But right now, SpaceX is testing an audacious lunar plan, a fully reusable Starship with over 600 cubic meters of internal volume, almost 100 times the living space of Apollo's module. 49 mission milestones have been crossed. If this unprecedented craft works, it could rewrite everything we know about deep space travel. How close are they, really, to launching the lunar revolution promised in those headlines? Starship's lunar variant is more than just a new spacecraft. It is a leap in what is possible for human exploration. Inside, over 600 cubic meters of pressurized volume stretch from floor to ceiling, dwarfing the cramped quarters of every lunar lander before it. That is nearly 2/3 the size of the entire International Space Station, packed into a single vehicle meant for deep space. Where Apollo's module gave astronauts barely enough room to stand, Starship offers space for living, working, and staging extended missions on the Moon. The design team at SpaceX did not just chase bigger numbers, they engineered a ship that could support new kinds of lunar science, longer surface stays, and real comfort for the crew. Every system, from life support to thermal shielding, is built with reuse in mind, not just for one mission, but for a new era of repeated journeys between Earth and the lunar surface. This focus on reusability changes the equation. Instead of throwing away hardware after every trip, Starship is designed to return, refuel, and fly again. That single decision reshapes not only how astronauts travel, but what they can accomplish once they arrive. The scale, the flexibility, and the sheer volume inside this vehicle set a new standard for what a lunar lander can be. 50 years ago, the Apollo lunar module touched down on the Moon with just enough space for 2 astronauts to stand shoulder to shoulder. Its pressurized cabin measured 6.6 cubic meters, barely larger than a walk-in closet. Every kilogram was counted. Every system was designed for a single-use. The entire module, from its spindly legs to its gold foil insulation, was discarded after one mission. Crews spent no more than 3 days on the lunar surface, working in shifts, eating, sleeping, and preparing for the return trip in a space so tight that even turning around required careful choreography. The Apollo lunar module's ascent stage, just 4.2 meters across, was powered by a single engine loaded with hypergolic propellants, which were simple and reliable, but toxic and limited in performance. Starship Human Landing System does not just scale up these numbers, it overturns the entire approach. Instead of a cramped, expendable cabin, the new lander offers a vast, reusable environment nearly 100 times larger. Where Apollo's mission architecture demanded a throwaway mindset, Starship is engineered for repeat journeys, with the ability to refuel and return to lunar orbit after each landing. This integrated stage design means the same vehicle handles descent, surface operations, and ascent, with no more jettisoned stages and no more one-way tickets. The shift from disposable modules to a single, robust spacecraft marks a break from every lunar plan before it, and it sets the stage for a fundamentally new era of exploration. Progress on the Starship lunar lander is not measured in broad promises. It is tracked step by step through a rigorous series of technical milestones. As of late October 2025, SpaceX reports that 49 Artemis-specific milestones have been completed for the Human Landing System. Each milestone represents a discrete achievement, verified by NASA before payment is released. These are not paperwork exercises. They cover hardware tests, software validation, and full system demonstrations. Among the completed tasks are micrometeoroid and debris shielding trials, ensuring the lander can withstand the constant hazards of deep space. Environmental control and life support systems have been put through their paces, simulating the lunar vacuum, temperature swings, and the unique demands of week-long crewed surface missions. Thermal management hardware has endured cycling tests meant to mimic the Moon's harsh day-night extremes. Cryogenic tank tests have become a regular feature at Starbase, where massive stainless steel tanks are loaded with super-chilled propellants and held at pressure for hours. These tests go beyond simple leak checks. They validate welds, structural supports, and the ability to keep hundreds of tons of liquid oxygen and methane stable in microgravity. Structural hold-down trials have pushed the vehicle to its limits, confirming that the lander can withstand launch loads, orbital maneuvers, and the force of lunar touchdown. Each completed milestone is a data point on a growing ledger of technical credibility. The tally is not just for show, it is the foundation that allows SpaceX to claim readiness for the next phase, hardware trials that will bring the lunar plan out of the test stand and into orbit. At Starbase, the rhythm of production is relentless. Stainless steel rings arrive by truck and vanish inside the high bays, reappearing days later as fully stacked starships. The welders, technicians, and engineers work in shifts around the clock, chasing a pace few believed possible in aerospace. Since the first test flights, SpaceX has launched 11 starships, each iteration folding lessons from the last directly into the next build. The failures are public and sometimes spectacular, but every anomaly is met with rapid redesign and immediate action on the factory floor. Successes are measured in flight miles and tank pressures, not PowerPoint slides. Flight 12 stands out. It was a complete mission profile that saw Starship reach its planned trajectory, deploy simulated payloads, and return data confirming that the upgraded Raptor engines and new structure could handle the stresses of an operational lunar mission. The manufacturing cadence behind these flights is just as important. With Block 3, assembly times have dropped, and the integration of 9 engine aft sections and advanced grid fins now happens in parallel with booster stacking. The result is a pipeline that can support the rapid-fire launch schedule needed for orbital refueling. The test teams at Starbase operate more like a pit crew than a traditional aerospace division. Turnaround times between tank-proof tests, static fires, and full stack launches have tightened to weeks instead of months. Each completed flight, whether it ends in a controlled landing or a hard impact, feeds a feedback loop that makes the next vehicle stronger and more reliable. This culture of iteration is not just about speed. It is about building the confidence that when the time comes, a fleet of starships will be ready to choreograph the complex refueling dance that makes the lunar plan possible. 12 to 15 Starship launches are required to deliver enough propellant for a single lunar mission. Each tanker docks in low Earth orbit, transferring super-chilled liquid methane and liquid oxygen through pressurized lines. The choreography is precise, with tankers arriving in sequence and each connecting nose-to-nose with the depot or the waiting lunar lander. Fluid systems engineers oversee the pressure-fed transfer using quick disconnect valves and automated docking adapters. This refueling campaign is mission-critical. To keep the propellant settled at the bottom of the tanks in microgravity, small thrusters fire in short bursts, creating artificial gravity and preventing gas bubbles from entering the lines. This process is called eulogy settling, and it is essential to keep liquid propellant available for transfer. Insulation and active cryocoolers guard against boil-off, holding the propellant at temperatures below -180 degrees Celsius. Even a 1% loss per day can mean the difference between a successful transfer and an abort. Every connection, every valve, and every thruster pulse must work flawlessly to keep the lunar plan on track. the stakes are critical. Mid-2026 is not just a target on a calendar, it is a hard deadline. The first full-scale orbital refueling demonstration is booked for that window, and everything depends on its outcome. NASA's Artemis 3 mission cannot move forward until Starship proves it can take on fuel in orbit, rendezvous with Orion, and support astronauts on the lunar surface. The countdown is now measured in months, not years. At the same time, budget proposals in Washington threaten to limit Artemis to a single landing, putting immense pressure on both NASA and SpaceX to deliver results before funding windows close. Certification for crewed lunar landings hinges on the success of this upcoming demonstration. If the refueling test slips, the entire mission architecture could face cascading delays, jeopardizing the chance to land on the moon before the decade's end. For the teams at NASA and SpaceX, every shift, every launch, and every test now carries the weight of this ticking clock. Right now, SpaceX is shaping how humanity returns to the moon, with hardware already built, and 49 NASA milestones behind them. If orbital refueling works, the moon becomes not a limit, but a launch pad. The next leap is not theoretical anymore. It is happening in real time. What do you think?